Hello class. So today we're going to be looking at Unit 9. We're just going to be starting out with inverses. Specifically, we're just going to look at whether or not there are inverses. And then we'll look a little bit more into determining the inverses. But for inverse functions, we kind of need to review what a function actually is. So, just talking about a function in math relations, or what we normally see, it's defined as a function if the relation for every domain value corresponds exactly to one range value. What this means is that for every x, there is one y. Okay, because if we recall, our domain values are x values, and our range values are y values. So, for every x value you have, we're only going to have one y value. Okay, so let's look at some examples of that with tables. Alright, so if I want to determine if these relations are functions or not, we need to figure out if every x value only has one y value. So to do that, if I have a single x of 1, it has a value. Okay, I have a single x of 2, it has a value. We're good. Single x, single x, single x. We have no repeats of x. No repeats. Of x, which means that every domain value, or every x value, only has one y value. So this indeed would be a function. Okay, let's look at this next one. Similarly, if we have this table's not the best, but we have our x and y here. We don't have any repeats of x. So, since there's no repeats, it's going to be a function. Okay, and for our last relation here, I want you to notice something. I have an x value, and I have another x value. X value. See how we have that repeat of 1 here? Okay. And then we have all the other x values are the same. Since I have this repeat, our input of 1 is repeating. So we have the point 1 comma negative 3 and the point 1 comma 1. Since there's a repeat there, I have this x value has multiple y values, so it is not a function. Hopefully we've seen this before. Just a little bit of a review. Okay? Now, this idea, it holds up with tables, but we can also find it with graphs. So, with the vertical line test, we should have, hopefully we've seen this a couple times now, but quick review. Our vertical line test, if I take my pen or pencil and I draw vertical lines up and down across my paper, if the line I draw only ever touches one point, then the relationship's a function. So for instance, let's look at our first relation here, the graph. If I draw a vertical line, we don't touch multiple times. If I draw a vertical line, we don't touch multiple times. Draw a vertical line, see it only touches a single time. Since it only touches one time, it's going to be a function. So this would be a function. Okay? Try to look at this next one and guess if you think it's going to be a function or not. Don't think it's too long, so just give you a couple moments here. Okay. Now, if I draw a vertical line through here, I touch 2 different times. Okay? Since it is intersecting at more than 1 point, it is not a function. Okay? And for our last one here, I want you guys to take a couple seconds, look at it, see what you think it's going to be. Oogie Joby. Alright, let's give it a go. So if I draw some vertical lines here, notice how my lines only ever touch a single time, no matter where I draw a line. Okay? Since it's only a function. Alright. Okay, so that's our functions. Now let's talk about inverse functions. Oh, I guess we're doing one-to-one first. So, a one-to-one function, which by the way, it just means it's going to be a function that has an inverse. It means that, first of all, it's a function, like we just defined. Can't be a one-to-one function if it's not a function. But otherwise, no 2 domain values correspond to the same range value. So beforehand, on our function, every x has one y. With our one-to-one, every y has one x. In fact, what this means is the property that we just found that we can't have any repeating x's for it to be a function, it's going to be a similar idea. To find if something's one-to-one, we want to make sure that there's no repeating y values. Let's see what this looks like with our tables. So if we want to determine if the table represents a one-to-one function, well, first things first, we need to determine if it is a function. Alright, so take a second, try to look at our table, see if it's a function or not. Okay? Alright, so for our first table here, since I have no repeating x values, it is a function. And since there are no repeating y values, it is one-to-one. So we can write that down. No repeating y values to be one-to-one. Make this nice and small. Oh, it's a since there's no repeating y values, it's going to be one-to-one. So let's look at our second table here. First, let's look at the x's. I don't have any repeating x values. That's good, so it's going to be a function. And for the y's, remember f of x is y, by the way. This is y. If I have any repeating y values, it is not one-to-one. So you notice how we have ones that are repeating here? So it is not one-to-one. So it is just a function. It is not one-to-one. Okay. I believe you guys have also seen one-to-one functions before, but it's good to see them again, because later in this chapter we're going to be looking at doing it algebraically. Sometimes seeing the tables in graphs beforehand can make it a little bit simpler for the ideas. All right, so we had the vertical line test. So now we have something called the horizontal line test. The horizontal line test will determine if a function is one-to-one. So it's going to determine if one-to-one. To have a one-to-one function, we have to have a function in the first place. So we're going to start by using the vertical line test we covered earlier. Afterwards, we're going to do something called a horizontal line test, which is the same idea as the vertical line test, except we're going to draw horizontal lines. Okay? So, for the vertical line test, if we start here on the first one, if I draw vertical lines, no matter where I draw the line, it only ever touches one time, so it's going to be a function. Determine if it's one-to-one, I draw a horizontal line, and notice how that touches multiple times. Since it touches multiple times, that's equivalent to us having that repeating of y values. So it is not going to be one-to-one. Okay? Now, let's look at our second graph here. So, if I draw a vertical line through here, because we want to start with our vertical line test, if I draw a vertical line, we get 2 points, so it is not a function. Since it's not a function, it can't be a one-to-one function. Even though, if you're looking at it, it does pass that horizontal line test, but since it's not a function, it can't be a one-to-one function. All right. Now, let's talk a little bit about inverse functions. So, the reason we're covering one-to-one functions in the first place, because if a function is one-to-one, then it has an inverse. Now, what an inverse function is a function that effectively cancels each other out. Okay? It's called an inverse when, if we have two functions, h of x and g of y, they're said to be inverses if g of h of x is equal to x. What that means is if I plug a function into another function, it's going to cancel itself out. They're inverses because they cancel each other out. Just like adding and subtracting are inverses because they cancel each other out, or multiplying and dividing are inverses because they cancel each other out. Inverse functions cancel each other out. They essentially revert. One-to-one functions f of x and g of x, they have domains x and ranges y, and the inverses have domains y and ranges x. So we're going to see this several times today. The domains and ranges switch. With an inverse function, to find all you're going to have to do is change the x and y. We're going to see a bunch of practice with that though. You're probably going to hear me say change the x and y multiple times today. Okay, but something to remember, they're reverse, so they cancel each other out. They're inverses. In a function, if it's one-to-one, it has an inverse. This is going to be important. Okay, so let's look at some examples. Okay, since the domain and range switch, to find the inverse function, you switch the x and y value. Okay, now, if we look at function f of x here, its inverse is f to the negative 1. What happened is if I have two functions, if x is their input, y is their output, you're switching the x and the y. All of my x values here became my y values. All we're doing is switching the x and y. Okay? At the same time as the x's are becoming the y's are becoming the x's. I'm just slowly underlining it. That's what I want you looking at. X's and y's, all they're doing is switching. So to notice, even if we had this in points, for instance, remember x comes first, then y. In this case, you would switch. It'd be y and x. All we do to go from the function to the inverse function from a table or a graph is we're going to switch that x and y value. Even algebraically, that's how we're going to end up finding the inverse functions, is just switching those x's and y's. This is super important. Find the inverse, switch the x and y's. Repeating it a bunch. I hope it sticks in with you. So let's look at what this looks like for a graph. Here, we can even color code this. Let's let the blue graph here on the left be f of x. Okay? So, if I have a graph, the blue value here is our original function. To get the inverse, we're changing all the x and y values. So if it starts here, well, 0, 0, if you switch those, it's still 0, 0. Oop. Not the prettiest. To get the inverse, which is my red graph here, all that we have to do is change the x and y values, which if you think about it, you're making y equal to x and you're making x equal to y. We're inversing that x and y value. So for a function to graphically to recognize it as an inverse, they're going to be reflected like a mirror. This is like a mirror looking back on the other one. Like a mirror. Okay? It's going to be flipped, reflected back across that x and y axis. So we'd see this with a linear function, for instance. If my original function was this red line here, if I flipped my line across the y equals x, which is our green line there, the distance from here to here is the same from there to there. It's just flipping and going across. It's like our red function is looking in a mirror back at the blue one. Just flipping across that y equals x axis. We're going to repeat this topic a little bit later. Just try to get to sink in a little bit. But in general, to see inverses graphically, we're switching the x and y's, and what that does is it flips it across the y equals x axis. Okay. So, let's look at an example. If I have a function, p of x is equal to 3 to the power of x, so exponential functions, and its inverse, p to the negative 1 of x is equal to log of 3 of x. We'll look more into logs later in this unit. Don't worry about it too much right now. Just know that they're going to be inverses of each other. I have my graph here. I have my orange line and my blue. If I wanted to draw a line that represented where they were flipping, it'd be about, that's a little lag. If I draw little points halfway in between these two lines, are the two functions, roughly where they're going to meet. So the distance from the top and the bottom is the same. What ends up happening is we're actually going to get that line straight through y is equal to x. So our linear function. Starts at 0, has a slope of 1, so we get the basic function y equals x. For the equation of a line of reflection, remember, is like a mirror, it's going to be y equals x for all inverses. Hopefully you're getting a little irritated of hearing me say that. Hopefully we can get to sink in there. Okay? Now, I want you guys to take a minute, try out and see which one of these functions, first of all, are functions, and then if they have inverses. Give you guys a couple seconds, okay? So if you had a chance to give it a go. Our first table here is a one-to-one function, so we circle it. Our exponential functions look something like this, if we remember. It passes the vertical and horizontal line test, so it's going to be one-to-one. One-to-one function. Our quartic equation here, actually, what is that? 1, 2, 3, 4, and it bounces. So I guess that'd be a 6-degree polynomial. But horizontal line test, so it's not one-to-one. Cross it out. On the bottom here, it's one-to-one and a function because it passes both the vertical and horizontal line test. So that's one-to-one function. Our other one here, let me erase to show you what the equation actually was. We had a quadratic. And if you remember our quadratics, they look like big U's. They're U's or N's. Oh, looks like the functions or the program isn't too happy. Give it a second. Oh boy. Here, let me pause. Oh, there it goes. So, okay. But our quadratics, they look like big U's or N's, so they're not going to pass that horizontal line test. So not one-to-one. This one's a little tricky because you got to know what the graph looks like. And then with our points here, 6 repeats as a y value, so it's not one-to-one. It is a function though. Okay. Now, let's see if we can try to blitz through the second one a little bit, because this one's a little bit of a shorter lesson. So we're going to combine them. So for lesson 2, represent inverse functions graphically and in a table. Okay. Before we had to recognize them, now we're going to switch the x's and the y's. Okay. Just a little bit of review here. We're doing it again. If I want to draw the line of reflection, all inverse functions reflect across y equals x. Every last one of them. All of them do. All. Very important. Okay? Let's look at another one. So, let's talk about whether or not functions, why the horizontal line test even matters, to be honest. So, our original function here is the red. It passes the vertical line test, so it's a function. But it fails the horizontal line test, so it has no inverse. It is not one-to-one, so it doesn't have an inverse function. The reason it doesn't have an inverse function is because the inverse, remember that's when we flip it across to the y equals x, is not a function. What that means, because we failed the horizontal line test on the original function, that means we're going to fail the vertical line test on the inverse. Because we're switching the x and y, it changes if we're going to fail the vertical or horizontal. Okay? Alright. So, let's look at a couple examples. We're just going to do one of these. We don't need to worry about this second one here. So I'm going to blow up this graph a little bit. Might make it a little bit easier for us to see. And then we're not going to worry about this one side here. Don't worry about it. We'll just do the one example. Okay? So, note, define the inverse, switch the x and y. Scoot that over CCI. So, let's figure out what our original function is in red. To get our x values, we can pick whatever values we want. Then we do -1, 0, 1, and then maybe 2, 3. So to get my y values, I'm going to plug x into our function. Okay, so I want you guys to take a couple seconds, plug your x values in, get some y values. And then, once you have your y values, I want you to plot those points on the graph below. Take a couple seconds, try it out. Okay, so these are the points we should have gotten. And if we graph these points, we have one at -1, -8, which is down there. We have 0, -1, right there. We have 2, 1, 2, 1. We have 3, 8. 3 is up to 8. Okay. If you remember, cubic graphs, I'll leave the points there since we drew them. Like something like this. And they go up forever and down. Now, to find my inverses, there's two things that we could do. This is my inverse function. In the next lesson, we'll learn how to actually solve for it algebraically, but this is our inverse. But if I want to just find it from a table, we can just switch our x and y values. So we'll do this one in blue. So if my original y value, or x value is -1, that's going to be my y value. My x value is what the y value was, so -8. All we're doing is switching the x's and y's. So it would be 0, 1. We'd have 1, 2, and 8, 3. All right, let's plot our points. So I have a point at -8, -1. So right there. We have a point at -1, 0, -1, 0. We have a point at 0, 1, 0, 1. Point at 1, 2. So 1, 2. And then we have a point at 3. Oh, and it's, wait, did we, at 8, 3. So 8, 1, 2, 3. Okay, connect these. So it's just flipping across that y equals x graph. Okay, so what happens, once again, if we have an inverse function, x's and y's flip, and on the graph, the x's and y's flip, which looks like reflecting across that x and y axis. Oh boy, looks like program doesn't want to respond again. Okay, we'll pause, give it a second to relax. Oh, never mind. School computers are always a fun time. What is it doing? Alrighty then. Oh, ignore this here for a second. Okay, so we have a table of values asking for r of x is equal to, they give us a function, and they want us to graph the inverse of that function. Apologize for the computer difficulties. It's been fighting me. But so I can pick any x values that I want. Technically, we could pick any y value and then solve for x, but it's easier just to plug the x value in. So when I'm picking x values to plug in, let's try to be smart about it. If I plug in 0, anything times 0 is going to be 0, so 0 plus 6 is just going to be 6. And then I can pick any other x values below or above it, but I kind of want to get rid of that fraction. So if I multiply by factors of 3 for my x values, it's going to give us a little bit nicer numbers. So I'm going to pick -6, -3, 3, and 6. Oh boy, there it goes again. There's something else today. 3 and 6. If you picked other numbers, it's okay. The answers will still be valid. It's just factors of 3 are going to cancel out that fraction and make it a little bit easier on us. So if I plug in -6, we have 2/3 times -6 plus 6. Well, 2 times 6 is 12. 12 divided by 3 is 4. So we get -4 plus 6 would be -2. Same idea, except plug in. Oh, there it goes again. It's making the really stretching the end of this video. Why is programs having such a hard time today? Alright. Okay, so if I plug in -3 times -3 is -6. -6 divided by 3 would be -2. -2 plus 6 is going to give us 4. Oh, actually this previous one here should have been a +2 as well, because we'd have -4 plus 6 would be +2. Okay. Similar idea on this side. If I plug in +3, we're going to get 2 plus 6 will be 8. And if I plug in +6, I'm going to not, since it messed up last time, I guess I'll write it down here. 2/3 times 6 plus 6 by 3 is 4. 4 plus 6 is 10. Okay, so that's our original function. Now, for my inverse function, so if we have r, by the way, the notation for that is a -1 on the outside here. We've used it a bunch, but just in case that you missed that. And then all we have to do is switch the x's and the y's. Oh, there it's going. We're switching the x and y values for our graph. So my y value is actually going to be 2 for my first point. So 2, and the x value will be -6. Okay, next point. X value is 4, y value is -3. X value is 6. Remember, we're switching them. And then the y value is 0. We have 8, 3. 8, 1, 2, 3. Then we have 10, 6. So we have our linear function here. Okay. And then if we did want to, I guess we can graph the original just to kind of show that it's still going to flip that x and y. It's going to be at x is -6 and then +2. And it's going to be -3, +4, and then it's going to be 0, 6, and then 3, 8, and 6, 10. If you notice, our lines are slowly converging there, and they're just all reflected across that y equals x. It's like a mirror. Your question was specifically asking for blue, so that's all you'd need to know. But in general, it's just want to show that again. Important things to know for a little wrap up. Inverses, switch your x and y's. Functions, you can't have any repeating x's or the vertical line test. And then one-to-one functions, which tell us if we have an inverse. You can't have any repeating y's. Use the horizontal line test. And then graphically, we're reflecting across that y equals x function. All right, hope you guys have a great rest of your day. Apologize for the technical difficulties today.